Hi, welcome to this new video wherein we will draw shear force diagram, minimum diagram using the differential relationship based approach. In the first example, we have this span AB and then BC. For span AB, the UDL is acting upwards, and for the span BC, the UDL is acting downwards. The first step is to determine the reactions. So just for the sake of determining the reactions, you can replace this UDL with equivalent concentrated load acting at this midspan. Okay, so that is straightforward. One can do that. One will be able to find the values of these reactions as usual, right? And then the positive sign convention, we have a quick recap of it here. So this is the positive sign convention for shear force, and this is the one for bending moment. If you consider the left phase, the force which is acting downwards, and if you consider the right phase, the force which acts upwards are taken to be positive shear forces, right? So that's what we follow here. And the loads which are acting upwards and the displacements which are upwards are taken to be positive here, and the rotations which are counterclockwise are taken to be positive here. And this is the important reaction relations. These are the important relations what we are going to use here in this video. In the first video regarding SFD and BMD, we have derived this expression as well. Okay, mind that we have a negative sign here. So in order to first draw the shear force diagram, we can start drawing the ordinates at both ends because we know the reactions at both ends. Okay, so here we have a downward force, which means positive for us here. Similarly, here we have upward force, which is also positive for us here. So at both ends, we can draw the ordinates. Okay, and how about the variation of shear force for this span? Should it be like this or should it be any other way? Okay, here it should be facing like this. Okay, only then, and it should be a straight line as well. Only if it is a straight line, the slope is going to be constant throughout. Okay, and mind that this is positive slope or negative slope for us. This is a negative slope. Clockwise rotations are negative slopes for us. Okay, only if it is negative, then we can attach this negative sign to it and we can relate it to the intensity of load acting this span. Mind that this is upward force, which means positive. So only if the slope is negative, you can add negative to it, which will result in a positive intensity value here, right? Therefore, for this span, the variation of shear force should be like this. With the same logic, one can say that the variation of shear force for this span BC is like this. Okay. So therefore, can we just consider the shear force diagram like this? Is it fine? No, because we need to also determine what is the value of shear force at this junction. Otherwise, we also should see the other way of determining it is we need to see the variation of shear force in this span AB. Something like this is what we are going to determine here for this span AB. So in order to do that, one can have a cut section here as I'm showing here. Okay, I'm cutting across a section somewhere here, marked x1 units from the left end. Okay, and I'm showing the shear force acting upwards because this is a right cut section. Similarly, for the span BC, I'm doing the same, but I am taking a section from the right end. Okay, so I'm marking x2 here. See that I'm showing the shear force facing downwards because this is the left end. Why I'm doing that? Because this is the positive senses of shear forces for us. Then using the vertical equilibrium equation, one can write these two expressions for shear force and one can determine the location where the shear forces are becoming zero. So in this case, the shear forces are becoming zero. That means when I am starting the shear force like this, it is becoming zero at a location of 2.5 meter marked from the left hand here. And for this span, this is happening at a location of 1 meter marked from the right hand. Okay. So the shear force diagram should look like this. Fine. And I am showing that you can relate the slopes to the corresponding intensity of load acting on each span here. Okay. That's all it is. Then we will move on to draw the BMD here. So here we need to consider four portions of spans AD, DB, BE, EC. Why? Because each of them show a particular trend of SFD. Okay. So if we start with the span AD, we see that the ordinate is positive and maximum here and attains a zero value here, right? Then the slope of the minimum diagram should be such that the slope is maximum and then it becomes a zero when it reaches D, but with a negative sign, right? Therefore, if the ordinate is positive here, then the trend of negative slope in the minimum diagram should show that, right? So we see that for us, the clockwise slope is negative, right? So therefore, therefore, the variation of bending moment should be like this. Only then it will have a negative slope. And if we attach a negative value to it, then it will mean the positive ordinate here. Okay. So it has to, the slope should start with a maximum value and it should become 0 when it reaches this point D. Okay. So for each of this variation, you can pick accordingly which uh, trend of BMD should be. Okay. So for this span, it has to be like this. Only then it starts with a 0 value, and you see that this is a positive slope for us. So maximum positive value, and then when we attach a negative value, negative sign to it, it is going to represent the maximum negative ordinate attained here. Okay. And then for this span, it has to go like this. Okay. So it becomes 0 here. The slope is 0 here, which means the ordinate of shear force is 0 here. And this is a positive value. Okay. If the trend is like this, we will have a positive slope here. And then if you attach negative sign, it will correspond to the negative ordinates here. So that's the logic here. Okay. So you can construct the BMD using this logic, right? So you can determine what should be the variation of this bending moment for each of these portion. One can refer to the previous video wherein we shared this trends. Okay. After completing the bending moment diagram, we are going to also see how to arrive at the deflected profile. Now to do that, I am considering the relation m by e equal to 1 by r. Okay. That is 1 by r is the curvature here, and one can approximate the curvature as d square del y by dx square. Here del y is the displacement. So you can consider this curvature as rate of change of slope. And from these expressions, you can relate the bending moment to the curvature. That is, the bending moment is directly proportional to the curvature. If we consider a simple case wherein we take the equation of upward opening parabola, which is y is equal to x square, you can see that d square y by dx square, which is the curvature, is positive here. That means if the geometric figure has the upward opening trend, then it is going to have a positive curvature. That is the message conveyed here, right? So the two rules which we can use, which will be very helpful for drawing the reflective profile, is if the bending moment is positive, the curvature also should be positive as per this equation, right? Expression, I mean. And if the bending moment is positive, the shape should be facing upwards. Okay. To put otherwise, for us, the beam will be sagging and the vice versa is applicable. That is, if the bending moment is negative, then the curvature is negative, which means the beam should be hogging. Okay. So with the same idea, you can see that for this span, the bending moment is negative. That means it should be opening downwards. That is, the reflected profile should be opening downwards. And for this span, the bending moment is positive, which means the reflected profile should be opening upwards, or to put otherwise, sagging. Okay. So with this idea, you can show the deflection going like this from left hand through the left hand to the right one. Okay, right hand I mean. And other than that, we can see that here the top portion contains tension and the bottom one is in compression. It is ulta here. Okay, the top one is compression, is in compression, and the bottom one is tension. Why I am saying that? Because the bending moment diagram gets drawn on the compression side here. Okay, here the compression is downwards, so we need to draw the bending moment below the neutral axis, and here we see that compression upwards. That means the bending moment is drawn above the neutral axis. That is the connect here. Okay, let's move on to the next problem here. The only difference is at this location B, I am adding a considered load of 7 kilonewton. Okay, so how does it affect the shear force and bending moment diagrams? What we are going to see here, the first step is to determine the reactions as usual. But for the configuration here, we have a reaction of 0 at the right end here. Okay, unlike the previous problem. And the value of the reaction at the left end is 7 kilonewton. So this diagram looks okay. It is not similar with the previous one. Just at the left end, we have a positive value, just similar to the previous problem. But at the right end, it is 0 because the reaction is 0 here. Okay. These trends, however, remain same, right? These are the trends what we have seen in the previous problem. So as I have done the previous problem, one can locate the variation of, or one can locate the place where the shear force is becoming 0. And for this portion, in this case, you won't have a location where the shear force is becoming 0 in this span BC. You can get that from the equation what you can write here for the shear force. Okay, it is obvious, one can understand it. However, we see that there is a jump here in this value of shear force. Why does that happen? It is relatable to the shear force applied here. Okay, so the message is whenever there is a constant force acting here, you see that there is a jump in the shear force diagram at the same location, right? So this value is equal to, the jump value is equal to the considered load applied here, okay? How does it affect the bending moment diagram? So the trend remains same, okay? However, we need to consider only three portions here. In the previous problem, I told there are four variations of bending moment, but here only this three, okay? Maximum to 0, 0 to a negative max, okay? And then negative max to 0. So only we need to consider these three trends, 1 and then 2 and then 3, okay? And another point here is, even though the bending moment diagram is continuous here, there should be a slope discontinuity here, okay, of the bending moment diagram. Why? Only then it will reflect that there is a jump in the value of shear force at the same location, as these are connected through the expression dm by dx equal to minus v, okay? So that is the only point extra we need to consider here. Then with the same idea what I explained in the last problem, one can show the reflected profile like this, right? Because the bending moment is throughout negative, right? Which means the if the bending moment is negative, the curvature is negative. That means the profile should be opening downwards. Reflected profile should be opening downwards. Also see that here this is the tension side, this is the compression side, right? So we see that the bending moment is drawn below the neutral axis. Okay, that is the usual observation. And in the last problem, we are going to have a concentrated moment applied here, okay, rather than a concentrated force what we have seen in the previous problem. So again, find the reactions. You have a different set of reactions here. Then start drawing the shear force diagram. You see that the shape is same as what we have seen in the first problem. Why does it happen? Because the application of concentrated moment at this location doesn't affect the shear force diagram. It has a consequence only in the minimum diagram. Okay. So the shape of this remains same, okay, as of the first problem. However, we see that there is going to be a jump in the minimum diagram at this location. And again, here we need to consider four different portions, 1, 2, 3, 4, in order to draw the minimum diagram, because these four trends will have a consequence of the shape altering here for these four portions of minimum diagram. Okay, and this jump here should be related to the value of concentrated bending moment, concentrated moment applied here. That is the external load applied here. Okay, this jump is related to this value here. So that's all. That's how it is written. Finally, the reflection profile. You see that for throughout this, from this end to this end, this point to this point, the bending moment is negative. That means the reflected profile should be facing opening downwards. And from this point to this point, this is a positive bending moment, which means the curvature is positive, and hence the beam should have a sagging effect here, right? So opening upwards. So that's how we complete the reflected profile. It's always good to have a relationship between the bending moment and the reflected profile. That's why we are relating the reflection also, the reflection diagram also in this particular video. Hope this video helps. So we will also share this corresponding notes in our LinkedIn page. Go get it, and then please go through this one carefully and try to understand how it works. Okay, thanks a lot.